Yes, am I audible? Ali, Halima, Oishi?
Yes, ma'am.
All right. In the last class, we were discussing this question we were discussing now. We have started with this, right?
Yeah,
This
yeah.
much. Okay. So see, we have a pipe over here. I was discussing with you that the angle of incidence is there, it gets refracted because the pipe has different material. In fact, the pipe is made up of two different kinds of material. Inner is different, outer is different. Inner's refractive index is given, which is in fact denser. Outer is also given, which is rarer. Okay, and we can see it through the values, okay, directly, even if it's not mentioned, which is rarer and which is denser. All right. And coming to the question, what the exact question was? Question basically said that what is the angle of incidence for which TIR occurs? The previous question was, which we discussed, that what is the angle of incidence for which, not exactly the angle of incidence, it gave you the angle of incidence and it asked you the critical angle. Means just the condition before the TIR occurs. Okay. Now in this question, the question clearly mentioned that you have to find out the angle of incidence. I told you that if TIR is occurring here, if we have the angle of incidence over here, it gets refracted. Okay. When it gets refracted, here is the angle of refraction. Here's refractive index is known to us. This edge of the pipe's refractive index is known to us. So if we get the angle of refraction, we will be able to get the angle of incidence using the Snell's law. In order to calculate the angle of refraction, we can use the angle sum property. But how will we use the angle sum property? Only if we know what's the value of this I dash. And from this whole thing, we only know that I dash is greater than the critical angle because total internal reflection has occurred. And this is one of the applications also. We'll discuss this under the applications after this question. So as I said, we were discussing, okay, the refractive indices are over here. Sin I dash is greater than. Okay, we didn't read the question. See, this says that figure shows a cross section of light pipe made of the glass fiber of refractive index 1.68. Okay. The outer covering is made of material of refractive index 1.44. What is the range of the incident rays with axis of pipe for which TIR takes place? It says axis. Okay. So this will be greater than or equal to also. The last condition possible is equal to, but this is for TIR, it is greater only. Equal to means a little slight, almost equal value than the critical angle, means very slightly greater. That's why we put, because it says range. Otherwise, we just have the greater symbol sufficient, but put equal to also. So greater than or equal to this. Now coming to the triangle part also, I can say R plus I dash plus this 90. Like if I draw this small one, this is R, this is I dash, this is 90 degree.
Ma'am,
So I
can you go to the figure? 1 second. See, the light is coming from outside, right?
yes,
So there'll be a refraction in the outside plane, and then there'll again be a refraction on the inside plane also, no?
there can be a refraction if it wasn't exceeding, right?
Okay, so we don't
Simply,
consider that.
no, because that isn't occurring. TIR occurred,
Oh,
no.
okay, is this cut? This is cut part. Like the
Where?
incident light is coming from, like the
This
incident
is
light
the
is.
starting of the pipe.
Oh, okay,
This is air. Okay. So
okay.
in the pipe it is entering, it is going here. Now here, technically a normal refraction could have occurred like this, whatever we make. But again, if angle of incidence is crossed and all, whatever we've studied for TIR,
Yeah,
those
yeah, I got it.
conditions, it means are satisfied, so TIR occurred. Otherwise, the usual refraction could happen. Okay.
Okay.
So I dash plus R plus 90 degree is equal to 180 degree. We can say I dash plus r is equal to 90 degree. So this I dash angle is 90 degree minus r. So can I say here sine I dash, instead of I dash, in fact, I'll replace this. Now I can say sine 90 minus r is greater than or equal to sine IC. And 90 minus r is greater than or equal to sine IC. Now from here I can say this is cos r, which is greater than or equal to sine IC. In fact, we have this value with us. Sine IC is equal to 1 by NDR, this value 0.86. This is known. According to TIR, see, sine, I'll write it below. One more thing, I'll put it here in fact. See, sine IC, for the sine IC's part, according to the critical, because it is the critical angle, it will be 1 by NDR. So when you take the NDR value, this comes out to be on solvent 0.86. 1.44 divided by 1.6. This will be around 0.86. So your cos R is greater than or equal to the sin IC, which is 0.86. Like this also value you can use directly. Okay. Now, cos is there, sin R we need. So we can definitely use the identity. Like if sin R is there, then the problem is solved. That's what we want. If sin R is known, then done. Only sin I will be missing. So look, as I told you in the last class also, last numerical is if you have practice. I told you to practice that numerical only 2 to 3 times. If you have practiced, there's a similar pattern. See, cos R, getting cos R using this sin 90 minus theta identity. Then after this, we use sin square R plus cos square R is equal to 1. Right? So from here, what we'll get? Sine r will be equal to 1 minus cos square r under root. So I can say this whole thing is, this is cos r. So I can say sine r is equal to under root 1 minus cos square r, means 0.86 whole square. This is the value of sine r. How much will it be? Approximately 0.26. Okay, when you solve, I've solved it on the calculator, but while writing, try to just solve it. Values aren't difficult. So this is around 0.6. So sin r is known. Then what do? We apply the Snell's law. If we apply the Snell's law over here, see, what can we say here? Look, the refractive index of air into the sine of this angle will be equal to refractive index of this part into sine r. Okay. So here when we apply Snell's law, sine I into refractive index of air is equal to sine r into the refractive index of the denser part. Sine I is missing. This is 1. Sine r is 0.26 into ND is 1.68. This is 1.68. So this will be around, this value will be around 0.4368. So angle of incidence will be sine inverse 0.4368. So this is how we'll get the angle of incidence. Yes, tell me, class. Is this question clear to all? The steps and all? Clear or not?
Ma'am, how we get by 86 for signer?
By
1 by
0.86. 0.86
1
from the relative refractive index.
so
1
for 1
by
by
NDR, this, yes. 1 by NDR is NR by ND. This we did in refractive index. So see, 1.44 divided by 1.68, that is 0.86 from here. And then we put it for the critical angle formula. Remember, sine IC is equal to 1 by n. That n was actually NDR, no? Rarer was air, so we used to get 1 by n. But right now it's not air, it is 1.44. So 1.44 by 1.68. Got it?
Yes, ma'am.
Okay then. Class, did you write anything in the last class from this question? Or was everything left to be written?
We didn't write anything.
Okay. Then please write it. If there's any doubt in between, please ask.
And though the incident light is not going through the pipe material, right? And they said the outer covering is made of material or a refractive index 1.44. But it's going from air, no?
It is going from air, yes.
So, and they're saying the outer covering is made of refractive index 1.44. So why do we take NR as 1.44 and not N of air?
No, see, NR and ND are taken for this point. TIR is occurring here. Look at this window. Only in this part TIR is occurring. So here the rarer part becomes this part and denser becomes this. That's why that part. Because that's a portion of TIR, not the usual Snell's law. No. See, when we applied the Snell's law, we took this as air and this medium where it was lying. You will check where the ray of light is present in the medium. This is the TIR scenario. Got it?
Okay, so we take like from which surface it's reflecting back, that's the R.
That's the
NR.
D. It
The
goes from
one
the
like the
denser to rarer.
above the
Which is rare. Whichever is the
reflection.
lesser one. Lesser value of refractive index is the rarer.
Okay.
Okay.
Okay. Yeah.
Ma'am, for TIR, I dash should be greater than IC. Why is it equal to IC?
Fine, Abedullah.
For TIR, this I dash should be like greater than IC. But why is it like greater than or equal
I
to?
see. That's what I was saying. That's no saying says range of angle, because the question said no ranges of angle. So this also will be greater than or equal to this. Range will be means you will just start from the critical angles value, and just the next value you will start I1, then I2, then I3. So for the complete range till I dash. Because the question said no ranges. That's why we have put it as greater than or equal to. Otherwise, for TIR, it's always greater. Even if you remove, that doesn't affect, but it's just that we are setting it the lower limit. Like from where are we starting? Okay, just for that part.
Yes, ma'am. Ma'am, how is NR by ND equal to 1 by NDR?
Just Abdullah?
How is NR by ND equal to 1 by NDR?
This is the relative refractive index. 1 by, remember I told you 1 by NDR is equal to 1 by NR by ND. This is written, this is, wait. When you have the refractive index, the relative like N1, 2, we write this as N1 by N2. If it is NDR, we'll write it as ND by NR. Right? Now, if you have to write R by ND, we can write this as 1 by NDR. Now, why am I reciprocating it? Because TIR's condition says that sin IC will be equal to 1 by N. N is basically NDR. R goes up. That's why when usually medium is air, we write this as 1 by N. Got it?
Yes, ma'am.
Ma'am, can you go a bit up? Yeah, ma'am, you can scroll down. Ma'am, we just assume that cos R is 0.86.
Cos R.
Yeah.
No, this is according to the calculation, no? Sine 90 minus R is cos R, and sine IC's value is 0.86. So cos R is greater than or equal to 0.86. Why will we assume?
No, while calculating sin R, we took root of 1 minus 0.86 whole square.
Mm-hmm.
So there we are considering cos R as 0.86, no?
Yes, yes. No, you're saying because of the greater sign, Oishi.
Yeah.
Oh, see, greatest value we can't calculate, no? We'll, from ourselves, we'll calculate the minimum value. Equal to part we'll calculate. And then we can put a greater symbol that it can be maximum. Now, upper limit, we don't know because nothing is mentioned in the question. Like here also, cos R is greater than sin IC or anywhere that we have taken here. Also, I dash is greater than IC. Up to what? We don't know what's the upper limit. We just know that this is greater. So we just put up the greater symbol. Okay.
Yeah,
So
but if
because,
it's like
yeah.
same, then there will not be TIR, no? It will go 90 degree with the normal.
See, that's what I was saying. The minimum value that we take, this is exactly TIR's condition only. And for TIR, we
Oh, okay,
have
wait, I
have
got
the
it.
value.
So basically minimum, greater than the minimum value.
Yes.
Oh,
Okay. Now, Whenever ranges are there, no, try to put greater than or equal to when you can't calculate the entire range. Okay. Done?
Yes.
Done? Okay, now coming to the applications of TIR. So this first application, is it clear to all before the part that we have done the numericals and all? Yes, I'll say this again, I'm repeating, please practice such kinds of questions from TIR. These kinds of questions are, they have a basic similar pattern to be repeated. Okay, so try to follow it. Now applications of TIR, basically there are different layers of atmosphere.
Now,
Okay,
1 second. In the previous question, in the final answer, we'll put the equal sign.
yeah, you can put the equal sign. You can, like, just to show the range that we are starting from here now to greater, in order to just show the range part. If the question didn't say range, never put this equal to, because that's not the condition of TIR. Okay, then it will always be greater. Fine. But when it says range, so we have to specify one of the limits. Upper limit we don't know. Otherwise, we could have put sign this degree to that degree. है ना, यहाँ से वहाँ तक, but here we can't. Okay.
Yes.
Yeah, I was coming to the applications of TIR C class. Under the applications of TIR, you have various layers of atmosphere. And all these layers of atmosphere, they have different values of refractive index. Of course, it is very different because see, the atmosphere is very huge. This is not the basic small example of a glass slab or a prism that we have taken. Atmosphere is so huge. So at certain kilometers, the refractive index changes, which is very small according to the atmosphere. So what happens? The medium changes. Now see, let's say a ray of light is incident. This is the incident ray. You will have the normal. This will be refracted. This is the refraction angle. Again, here we'll have the normal and here we'll have the refracted ray. Okay, here we have. Now what happens? Here, let's say this is the portion where we, or in fact, I'll just draw one before this. Let's say this grazes over the surface. This is the critical angle. Now this is the normal. When you are exceeding it, what will happen? This will be totally internally reflected back in the surface. So what happens? Here you had the object present. Here your image will be formed. Just by the layers of atmosphere. So this is known as mirage formation. I think some of you must have heard of it. Especially in English literature, it is used as a metaphor also. In mirage formation, what happens is you see an object where you do not expect it to be. Like if I see a very shiny water surface, if I just see a water surface, I'll be able to see my reflection perfectly. If it's a river, if it's a pond. If I take a mirror, I'll be able to see my reflection properly. So these are the things where we expect, right, the image formation, because these are very smooth surfaces. But mirage formation occurs on an unexpected place. Reason is that this is occurring in the atmosphere. Atmosphere can be there anywhere. So what happens when you have very dry, scorching heat places like deserts? Many a times it appears the reflection from the sky. This goes, it refracts, finally total internal reflection occurs. So that object is your sky. Image appears on the ground, and in very, very hot, humid places, it appears as if water is present on the ground. When you go near it, then you realize there is no water present. Okay? That's just, this is also known as an optic illusion. This is optic illusion, because in reality there is nothing present, and it often confuses your highway roads, very hot, humid, in under hot and humid weathers, the when the vehicle is being driven over the highways, at a certain distance you see images of tree or something is present, but it's actually not present. That's why this is used in literature also for metaphors for something else and all. So what is mirage formation? When you have an object and different layers of the atmosphere act as different rarer and denser surfaces. So from the denser, see when why is this doesn't occur every time? Because to occur, it has to satisfy the conditions of total internal reflection. Now, when in the rare case, when the total internal reflection has to occur, means a critical angle becomes greater and the ray of light travels from the denser to the rarer medium. Then the TIR will occur and you'll see the image formation. Otherwise, you'll not see. If this was to happen, then everywhere we would have seen the images formed. This doesn't happen. So that is one of the application, which is mirage formation. Okay, like this you can see if this is a tree on the ground. Now, not a very bright, clear, beautiful image will be formed. A dull, light, uneven image is formed. But yes, something is formed, slight reflection is formed. And this is formed from the rays which are able to reach. Not all the rays are able to reach the ground back, okay, from the atmosphere. So this happens. So one of the best examples is not this tree, that desert example. In the desert examples, the water appears, which actually creates a lot of confusion among the people, and they travel distances to reach that point to take up the water and see. But it appears nothing. It's just plain sandy ground, and that's actually the reflection of the sky, which they are able to see. So this is one of the applications. And second is the brilliance of diamond. See, if I say, let's say this is a piece of diamond. So this, now all of you must be knowing, when you shine a diamond, or when the diamond is shown, or if you just move it a bit, you see light shines, right? Brightly the light shines. So what happens in the case of diamond is the light ray enters once. Now here at the surface, total internal reflection occurs. So it gets over the surface. Now here all this is constructed in a manner. Okay, diamond is constructed in a manner. It is created under a lot of pressure. High pressures are required that you must have studied in chemistry. And then when these are formed, all the cuts and all that are made in the diamond, they are made in such a manner that when the light ray strikes the diamond, here it gets totally internally reflected, so the ray of light is here. Then again it gets refracted, then the ray of light goes. Like this, the ray of light keeps on traveling. Okay, this is what appears. These are the rays of TIR, which is basically a thing. So it appears as if the light ray is trapped over a point. Okay, that is what is meant by TI. What is meant by brilliance of diamond when the diamond is shown. So value of critical angle here is 27 degree, and this is a very small value of critical angle. 27 degree is easily achievable, and this is a specific value, and it is almost 27 degree. Means this is not a fixed value for diamonds. So we say light is trapped, refractive index is high. That's what it is. Okay, that's why it appears as if the light is just rotating inside a small piece of diamond. Then coming to the totally reflecting prisms. Okay, totally reflecting prism. See, prism we'll be doing in detail separately. You have a topic, prism, dispersion of light and all. We'll be doing it at the end when all the topics are over. In fact, after optical instruments, we'll try to cover this topic, prism. So in a totally reflecting prism means you have the object, the light ray passes through the prism, and the images formed. That's the simple. Okay. Usually prisms are used for dispersion of light. That's a very good advantage of it, and a lot of things that we'll see in prism itself. Angle of deviation and all will come. Now, how to reflect a ray? How to deviate a ray? See, it depends on the orientation of it. From which side have you let the object put? Now, see, if this right angle prism means one of the angle is 90 degree, other two angles are 45. 45 degrees definitely. Total has to be 180 degree. Isosceles prism, both the angles are equal, but they can be any, like 20 degree also, 30 degree also. But yeah, when you have equilateral prism, that is when the angle of prism is 60 degrees. So 60 degree, 60 degree, like this you have, okay, 60 degree each for it. But if I have 30 degree here, 30 degree here, this will be 120. Like this, you can just make up it make up for it when the prism's angles are given. But here this is right angled prism because one of the angle is specified as 90 degree. Now, if you have to reflect the light ray by 90 degree, put the prism first in this manner. That one of the faces here and the hypotenuse is on the opposite side, and you put the object here. Let's say this is our object. Now let's see the light rays. See, the first ray of light will come here. The second ray of light will come here. Okay, so this will come here. Then what will happen here? TIR occurs and this gets passed over. Here also TIR occurs and this also gets transmitted like this. This moves. So what happens? The image created is in this manner. So this is the object. This is the image. Look, this is present. This is this is how it is deviated by 90 degrees. Okay, shifted by 90 degrees. So this depends on the orientation of the prism. You change the orientation, the reflection can be changed, and it can be in some random angles also. Now let's see this. This is 90 degree. This is 45 degree. This is 45 degree. Now the light, let's put the object here. We are reflecting it by 180 degrees. So the first ray of light enters, the second ray of light enters. These are constructed in such manners that total internal reflection occurs. Okay. Otherwise, see, these are done by the manufacturer themselves. The diamond part, these prisms and all, they are constructed in a manner that more than the construction part, the object is kept at such angles. All these are calculated experimentally. That's why we have the final concluded data. That's why we are directly using it. And you also remember these prisms as it is. Numericals can come from this, but directly based on prisms, it's different. In prism part, we'll see those numericals. Now see here at this surface, here at this surface, TIR occurs. Okay. So if TIR occurs, this goes here. This also, if TIR occurs, goes over this side. Now here also TIR occurs. At this surface also total internal reflection occurs. So this ray of light gets again reflected. This also gets reflected. So see, this is the image formation. This is object, this is the image. So see, object is like this, image is like this, angle is 180 degree. It has got reflected. Is this one, Oishi, you had a doubt in the reflection of prisms also? What was your question? Share your question. It can be
Yeah,
discussed
ma'am,
right
one
now.
second.
And the final application which you have studied in this numerical, optical fibers. Have you heard of those? Mouse, optical mouse. In computers, these are used. Optical fibers are used there. Light is shown, so it keeps on getting totally internally reflected in from the denser to the rarer and all. So that's why the light is shown. So this is also one of the applications. This is used in computers, especially the optical mouses that are present. So these are the examples, a few examples of TIR. Please write it, all of you. That completes your total internal reflection. Now mirrors and these TIR and all are done. So we'll have spherical refracting surfaces now, the next topic.
Ma'am, can I tell you the question?
Yes, please type it in the chat box or just share the picture of it. It's better just share the picture of the question, no?
Ma'am, is the speed of light in glass independent of the color of light?
Speed of light of
In
what?
glass. Speed of light in glass is independent of color of light?
No, this depends. Only frequency is independent.
Oh, okay. Ma'am, one more question. If the refractive index of denser medium increases, how will the corresponding critical angle change?
Refractive index of what increases?
The denser medium
See, if the
increases.
denser increases, no. Look, we have the value of 1 by NDR means we have uh, this rarer above and denser below because we have shifted it. This is basically equal to sine IC. Okay, so see this sine IC is what? It is NR by ND. So how are they related? They are inversely proportional. So one decreases, other increases.
Okay.
Ma'am, it is approximately equal to 27 degree, right?
What?
Here critical angle is approximately equal to 27 degree, right?
Yes, yes, more or less it's almost equal to 27 degree. Okay, in your first question, what is your doubt?
I didn't understand how we got the angle.
Which angle?
The incident and all.
See,
Mm.
there is first M in that strikes, which gets totally internally reflected in the right angled prism. In that,
Yeah.
are you asking?
No, in the bottom one.
In the bottom one, which angle?
Is it because like it's 90 degree when it's striking and then that's 60 degree? That's how it came, right?
You're asking about the below.
The
Hope you
30
get
degree,
this
the 30
45
degree.
degrees. Just you know why these will be 45 degrees.
Yeah.
Okay, then you're saying this strikes this surface and here occur TIR occurs and this moves further. So this is perpendicular, this is 60 degree, this is 30, this is 90. See, this is because of symmetry. There is no physics in this. See, the first two angles are 45, 45 each. Right? First two are 45, 45 each. Because 90 degree, 45, the rest angle will be 45. This is clear? The first two will be 45.
Yes. Yeah. I got
Now
it.
see, the light ray goes and it strikes. Now the light ray is moving at 90 degree and it is moving, right? So when it
Yeah.
strikes, see, if you look at the angle sum property, one angle is 90 degree, one is
No,
60 degree.
that's 60 degree, you know, when it's like striking and going out.
Because this is the normal. The dotted lines which you have drawn, that is the
Yeah.
normal. Okay. Like this, you have drawn the normal rays.
Yeah.
Now see, when you have drawn the normal, it means with the surface, normal means only this total is 90 degree. So if it is
Yeah.
30, this will be 60.
Yeah.
Okay,
And
if
then when
it's
it's going out,
when it is going out, let me look. This is coming. So angle of incidence will be equal to angle of refraction. So 60 degree,
oh,
laws of reflection.
yeah. Okay. Can you explain the second one? I think that's more confusing.
Let me look at it. Wait.
Okay.
Okay, this one, this three light rays, red, green, and blue one. This is a question from the previous year board paper. Okay, we'll be discussing this. I think it is one of your one of your assignments. See, calculate the critical angle for all of it. What you will do is you will calculate the values of critical angles for all of it. Okay, and what is this? This is a glass prism. A refractive index of the prism for red and all. Okay, these are given to us already. Now see, what you do, you calculate the values of the critical angles first. Fine. Now you check which of them, for this you'll have to calculate all the are the three refractive indices given? 1.39,
Yeah.
1.44 for green, excellent. Red is 1.39, then 1.44, then 1.47. Okay. So that is for the blue one. So see, green and blue will almost have the same critical angle, almost, because 1.44 and 1.47 are there, though values will be different for all of it. Okay. Now, what you do, see, here what's the critical angle? This is again a right angled prism. So like your previous question, Oishi, the critical angle
5.
here will also be 45.
Yeah.
So what you do, you calculate the individual critical angles. Whatever is greater than it will be refracted, and probably it will be the red one only, because see, blue and green are similar. But that please do through the calculations. Got it? You calculate the if whatever a value of critical angle is exceeded, that will be the TIR. If not, then that will
So if the
pass rate.
refractive index is more, then it will undergo TIR.
Refractive index
It,
नहीं,
like
critical
of
angle.
the color.
Yes. See, refractive index is more, critical angle will be less. Right.
Yeah,
Critical
okay, yeah, yeah.
angle lesser. So yes, red light. Answer is red light, 100%. But
Yeah,
check
okay.
it to the calculations from. Just on the prism, should I scroll down?
Last one. Done.
Then
Ma'am, this optical fiber I'm not able to understand.
what?
This optical fiber.
Yeah.
It's image formation I'm not able to understand.
Image formation. Image formation nahi hai. See, here the light gets trapped. Like, see, light enters, total internal reflection occurs. So it gets reflected. Then again TIR occurs, so it gets reflected. Again, like this keeps on occurring throughout the wire. The wires are constructed in this manner. So that's why light is there in the optical mouses. Okay, because this permits, means other reasons are also there, but this permits the optical fibers. They possess the ability to have PIR. Okay, image formation is not occurring. The light ray will keep on moving. Like this is just a small segment of the wire. Wire को पूरा कर लो, पूरा हो जाएगा. Okay,
Yes, ma'am. Done.
done. अच्छा. Now the next is spherical refracting surfaces. For your major portion of the chapter is done. Now we are moving towards the surfaces, and then this will continue towards the lens part. Okay. Now, when we talk about the spherical refracting surfaces class, I said that we have a glass sphere, and from this glass sphere, we cut the portion, we silver it on one side, and that creates a mirror. Now, what if we don't silver it? We just keep this glass portion as it is. So what happens? Refraction will occur because one medium is glass, other medium is air. So what we'll have, let's say this is a spherical glass sphere. Now I have cut a portion. So this is a convex surface. This is the radius of curvature. Here you have the denser refractive index. Here you have the rarer refractive index. Similarly, you have the concave surface, denser error. So there are four possibilities of cases. Okay, what do we try to do here in spherical refracting surface? It's a very, very short topic. Basically, you need to know the derivations. Two derivations are there, one major, other one is exactly similar to that. And in this topic, questions come based on that derivation, means the formula that you obtain. So it's a small topic. But yes, if multiple surfaces are given, that's the problem with ray optics. They can give multiple glasses, multiple lens, multiple mirrors, combinations of lens, mirrors, and all. That makes the question tough. So practice that only will help. So in this, we try to establish a relationship between the object distance, image distance, radius of curvature, and both the rarer and the denser refractive indices. So there are four cases that are possible. When the refraction occurs from the rarer to the denser medium, means object is in the rarer, image is in the denser. Then when the object is in the denser, then rarer. And for both convex, concave, convex, concave. So we'll discuss the one where the refraction occurs from the rarer to the denser medium. Okay. This I'll explain you later. First, write down this introductory part of this.
Ma'am, so both real and virtual image can be formed.
Yes, both real and virtual images can be formed here. Because we'll see one question also we'll see, because many a times no, when you get the complete glass, one refraction occurs here and another refraction occurs here. So this image becomes the virtual image and this will become the real image. Many a times these things happen. Okay. Done?
Yes.
Have all of you written? Okay. Okay, I'll stop here. In the next class, we'll meet then. All right. Only Ali has done the assignment of EM waves. Please class submitted. We have to discuss the assignment of EM waves. I'll be discussing it in the next class. I thought we would get time at the end, but in the next class now I'll be discussing all the 3 assignments of EM waves. So rest of you, please share the assignment. Okay. All right then. Thank you. Okay then.